Hello there, Mr. Sutton here, bringing you the Algebra 2 11.1 Part 2 homework solutions on defining and using sequences and series. In this one, we're going to focus more on the series end of that. The first few problems, we want to write the series using summation or sigma notation. So for this, I need to know really three things. What are my lower and upper limits of summation, and what's the summand? What's the rule? So let me start with the lower limit of summation. So I'll write my sigma symbol and I'll put I equals 1. I just start with 1. I might need to change that later, but it's always a good starting point because everything goes easier if I equals 1 as your beginning. So what is the rule that's going on here? So we've got 5, 11, 17, 23. It looks, if I take a quick look at this, like we're adding 6 every time. So that means I've got some kind of multiple of 6 sort of action going on here. So if I just write out the multiples of 6, so 6, 12, 18, 24, 30, it looks like that's pretty close to the series we have, only all the numbers of the series are the multiples of 6 minus 1. So this would be 6 minus 1, 12 minus 1, 18 minus 1. So in general then I'm going to write 6i minus 1 for my summand. And then for the upper limit of summation, since I equals 1 is my lower limit, I can just count the number of terms and that will be my upper limit, so we'll put 5 for that. To put this in summation notation, let's start with our lower limit of summation. So I'm just going to use 1 for that in the early going here and hope it works. So for my summand, my formula for the nth term, taking a look at this, it's a fraction, so I don't see any obvious thing that we're adding or multiplying by to get the next fraction. So let me instead look at the numerator and the denominator kind of separately and see if there's a pattern in each of those. So for the numerator, we've got 1, 2, 3, 4. So that's literally just adding 1 each time. So I can just use I for my numerator. That'll give us 1, 2, 3, and 4. And for the denominator, we've got 4, 5, 6, 7, so we're still just adding 1 each time, but we're not starting with 1 anymore, we're starting with 4 instead of 1. So for this 4 to get back to a 1, I would need to do an I plus 3. And then we'd have I plus 4, I plus 5, I plus 6. So we have I over I plus 3 giving us this pattern. And since this is going forever, the dot 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 tells us this is an infinite series. That means infinity is my upper limit of summation. Let's try to write this series using summation notation. So let me start with a lower limit of I equals 1 for this, and we'll just kind of go from there. So taking a look at these numbers, just to see if we're adding the same thing every time, we're adding 3, then 5, then 7. So this is not one of those multiples kind of patterns. We're not multiplying by the same thing every time either, so it's not an exponential pattern. So what could be going on? Well, let me write out the perfect squares and see if there's some kind of relationship there. So we've got 1, 4, 9, 16. So it looks like all of these numbers are actually just all the perfect squares with 3 added to them. This is 1 squared plus 3, 2 squared plus 3, 3 squared plus 3, and so on. So in general then, I can do I squared plus 3 for my summand. And since this is an infinite series, I'll use infinity as my upper limit of summation. For the rest of the problems on this problem set, we're trying to find the sum of the series that's given in summation form. And we're always on the lookout for shortcuts if we can. This is one of those shortcuts. This is the summation from I to n of just one kind of situation. So the formula for that is that's just going to come out to whatever your n, your upper limit of summation is. You're basically just taking 35 of these ones and adding them together. So that's just going to be 35. To figure out this sum, there's a couple of ways we could do it. We could try to use some shortcuts by splitting this up into a 2i and a negative 9, and then using the summation of I and the summation of 1 with some factors taken out. But that's a lot of kind of mental work. Since there's only 6 terms in the series, I think it would be faster just to write this as a formula in Desmos and just add F1, F2, F3, all of those together. So that's what I'm going to do. So let's let f of I equal 2i minus 9. So then we just need to do f of 1 plus f of 2 plus f of 3, f of 4, f of 5, f of 6, all of those. So let's go to Desmos and take care of that. So let me define my function. Let me move it so I can actually see the function. There we go. So we've got f of, we'll just call it x, equals 2x minus 9. I feel weird putting an I in there. All right, so then we've got f of 1 plus f of 2, f of 3, f of 4, f of 5, and f of 6, and that's a grand total of negative 12. On this problem, we're trying to find the summation from 1 to 16 of n. So this is actually a shortcut kind of problem. This is a summation of I sort of shortcut. And remember, the summation of I from 1 to n is just n times n plus 1 over 2. So instead of like doing 1 plus 2 plus 3 plus 4 and doing all that, we can just quickly plug in this case, 16 is my n value. So 16 times 16 plus 1 over 2. And I might even be able to do that without a calculator, but just to be on the safe side, let's just plug that in. So fraction, 16 plus 1, also known as 17, all that divided by 2, and that's 136. For this summation with n squared minus 1, we could, if we wanted to, split this up into n squared and minus 1, and then use a couple of shortcuts. But given that we're only doing 5 terms here, it would probably be faster just to define this as f of n equals n squared minus 1, and then just do f of 1, f of 2, f of 3, and just add all those together. So specifically, I'm going to do f of 1, 2, 3, 4, and 5, and add all those f ofs together. Let me do that on Desmos. So let me first define f of n as n squared minus 1, and then we'll just do f of 1, f of 2, f of 3, f of 4, plus f of 5, plus all those really, and that comes out to 50. In order to find this summation, I think the fastest way to do this is going to be to define this summand as a Desmos function. So let me just let f of I equal 9 minus I cubed. And then on Desmos, I'm just going to do f of 2 plus f of 3, basically all the f of all the integers between 2 and 7. So 2, 3, 4, 5, 6, 7. So let's go ahead and do that. So I've got f of, I wonder if I can use I. F of I equals 9 minus I cubed. Well, I guess we'll see if this works. And then we've got, again, f of 2, f of 3, f of 4, f of 5, and then 6, and then 7. A little bit tedious, but easier than doing it by hand. So that's negative 729, apparently. For this summation, we have 1 through 18 of n squared. So although we could define f of n as n squared and then do f of 1 plus f of 2 plus f of 3, that would be kind of tedious with this many terms. So instead, we're going to use our shortcut formula, summation from 1 to n of I squared. Remember, that was really n times n plus 1 times 2n plus 1, all over 6. So in this problem, the n is our upper limit, so it's 18 in this case. So we have 18, 18 plus 1, and 2 times 18 plus 1, all over 6. And I can run that on Desmos. So let's do a fraction, and up here we've got 18, 18 plus 1, and then 2 times 18, close that parentheses, plus 1, close that parentheses, all divided by 6, comes out to 2,109.